Hello everyone, it's December 28th. Alright, I need to finish today a little bit faster because I need to pick somebody up later from the airport. So, and I want to keep working a little bit. So let's see, probably depends because the last problem that we didn't do is a difficult one. So I'm not sure. So let's just handle this first and then see how much time we have. I think the time I'm gonna give myself is half an hour. Let's see what's gonna happen in half an hour. All right, single-threaded CPU are given n tasks labeled from 0 to n-1 represented by a 2D integer array tasks where tasks I is in queue time and processing time. Oh, okay. I actually remember I enjoyed doing this when I was taking the class, taking the geez, what's the name of the class? Computer system? Computer hardware? I don't know, but we deal with this CPU scheduling, and I wrote programs in C++ for crying out loud, simulating all kinds of strategies. The round robin, right? We have that, and we have a bunch of others. I forgot the name, but like, well, basically their priority, well, we consider their priority the remaining time of a task, and then you just decide. I think I set up a bunch of priority queues and decide which one to go first, and then pop it out, put it into a next queue, and things like this. That was interesting exercise back then. Yeah, that was at least 2 years ago. All right, anyway, we are a single-threaded CPU. And most, or we haven't even finished reading this. The ith task will be available to process at in queue time on take this amount of time to finish. Okay, yeah, that's basically write a scheduler for CPU. They have a single thread CPU that can process at most one task at a time, which is, yes, generally it is one task at a time. Unless you have multi-core, then you can do real parallelism, or you can only do concurrency. There's a difference between the two. Concurrency is, parallelism is, talking about real parallelism is executing multiple tasks at the same time, and it only happens if you have multiple CPUs, so you can execute multiple tasks at the same time, one per CPU, one per core. But concurrency, parallelism is concurrency, but concurrency doesn't necessarily mean it has to happen on multiple CPUs. You can do concurrent or quasi-concurrent on a single CPU by just pushing in and popping it out, pushing in and popping it out. Usually the CPU-bound tasks are fast, but the I/O-bound tasks are slow, like the network, calling internet, right? Input-output, typing, like all of these things are slow. So when it's reading from file from the disk, these are slow. So whenever it hits that, the CPU can pop this task out and just say, okay, this one is in the IO wait. So it go to a queue called IO queue, right? And then it'll pop in another one that can do CPU bound tasks. And then once the IO is finished, whoever finished first on the IO, and then there'll be IO queue will be popped and then go into the CPU queue for the task queue, and then it will continue execute. And this is how you do quasi-concurrency. And you can do this. Yeah, I'm actually just kind of refreshing what I learned a few months ago. And you can do this by completely letting the CPU decides, right? When you write programs, especially when I'm talking about Python, you can do the threading, right? You can do threading. And when you do threading, you basically send the tasks to the CPU, and it will decide when to pop you out, when to push you back in. But it can also do async IO, which basically saying that you will do cooperative concurrency. You are telling the CPU when you need to be popped out because you put async and await in there. So every time you await, the CPU will pop you out and then do whatever other tasks in the program. And then once the await is finished, it will pop back in. And that, my friends, are very, very fast, at least from what the examples I saw and tried. And async IO is amazing. But I tried to rewrite something in my internship completely in async IO. But dude, that one was hard. It's not hard, it's just because you have to do async IO in almost every part of your program. Like if you build something from scratch and then you just stick to async IO, and I think it will actually be fast, like really fast. But the one that I was dealing with, the overhead is just too much to change, because we have Postgres connection, we have Cassandra connection, and we have Elasticsearch connection. All of them, I think, yes, all of them have async IO. You can do async IO for all of them. There are libraries out there, but then you just have to change, because in that internship, all of these functions that talk to the database, they're in a factory, right? They are in one place. So if I want to switch that, dude, I have to write a complete new factory functions for dealing with the IO. So yeah, I eventually did not proceed. I remember I spent a whole night, I think I did until maybe 2 or 3 a.m. just trying to do this. It didn't work. It's like marginally faster. But I mean, you want to make things go fast, just run a profiler. This is the best, because you don't know. You guess, okay, I think the IO is slow and I'm gonna use async IO, I think I'll get it fast. No, that's not the low-hanging fruit. And then at that time, the low-hanging fruit was date parsing, parsing dates. Because parsing dates is, date time is just a whole mess of spaghetti. You don't want to do it, so you use a library to do it. And the library is, it can handle all kinds of things. But if your date time is more or less, or like in some certain places have already been handled, like well formatted, let's say to ISO format, they don't have to use the I think what's the date utility library in Python, which is very, very powerful, but it's just lordy, it's slow. It's so slow. Yeah, if you change that, you get 40% performance boost just by changing that one thing. And of course, some refactoring also helps. Right, anyway, that's not really important in this. All right, where am I? Oh yeah, we're talking about single-threaded CPU. Okay, the CPU is idle and there are no available tasks, remains idle for sure. If this is idle and there are available tasks, we'll choose the one with the shortest processing time. Okay. If multiple tasks have the same shortest processing time, we'll choose a task with the smallest index. Okay. Once a task is started, we'll process the entire task. That makes things easier. It says to process the entire task, and the real CPU won't do that. It can stop and then pop it, and then you have to push it back in. Okay, finish the task, then start a new one instantly, so there's no wait. The CPU itself doesn't have wait. In my model, does CPU have wait? Maybe it does. Maybe there is a wait in it. Return the order in which the CPU will process the task. Wait, what? That's it? I was so ready to handle, processing and then pop it out. But this looks to me is just a heap, a priority queue, and that's it. So it will process the shortest first. So our process. Oh, but we have the in queue time. Oh, okay, this is slightly more complicated. So we do need a heap, but when the heap is done, the in queue time should be the first, right? So we need the smallest in queue time. And then, my bad. So you have to sort by in queue time, and then, because this is 1, it'll take 2, and then this one's already in, and this one's already, I see. So 0 is first, then it's this, because at 1 time in, get 2 processes, we have 3, So the 3, we have both tasks in, so we need to pick this. And then after this is done, oh, actually this is not that easy. Okay, I was completely wrong. I'm at 5, so this one's in, so you push this one first, and then you push this one. Okay, this one's easy. Everybody is in at the same time. So you just do the smallest first. 3, 4, 4, 3, 2, 0, 1. Yeah, all tasks at the same time. That was fun. Yeah, this is fun. I mean, that class was, I mean, the teaching was not the best, but the homework was really fun. Those are the times that I program a lot. I don't program as much now. I mean, we do this every day, and I have my study and stuff. I have my app and stuff, but that's like nothing really. I shouldn't say that. This is actually quite fun every day. I really like it. All right, so we need a timer, right? We need a tick, right? We need a tick. So we have a ticker. We need to sort the task. Okay, we sort it. Tasks.sort. It automatically sort based on the first. Okay, and then what we do? What do we do? Maybe we sort in reverse will be easier because then it will pop out. Then we need a queue, right? So the first one get in, and then we get a timer, and then once it's done, we check, and then we'll push this in. Yeah. So we sort. I like to pop. Then you're changing the tasks. I don't know. Do you want to pop? You know what? I don't like the pop because if we can help it, we don't want to change the input values. But you're already changing the input values. All right. You convinced me. Okay. Time tick. Tick will be 0, right? And then we can say overall it's just while tasks, right? If we have task, and then we're gonna pop the current task. Okay, so we can say so every time we'll pop something from the task, and we'll have a result. Right, we'll pop something from the task, and then we'll see. Now we don't pop something from the task. We'll check. Right, we'll check the time. So we need to check is if time is smaller or equal to. Wait, no, it should be larger or equal to. Should be larger or equal to. You know what? Tick shall be tasks, because it would be -1, 0. It's the time, right? So we say if tick is larger or equal to tasks -1, 0, which means this one can be pushed in. And then we need to do, a queue. I have to call it heap. Okay. Then we need to do a heap queue.heap push. Well, when we push, we only need to push, the index. Damn, the index. All right, that's, we have to sort a task. Okay, so we need 3 things. We need its index as well. So for TP, right? TP in tasks. And then we need to do, ITP. ITP in, that's actually fine. IT in enumerate tasks. Nah, I need to TP. I need to get them out. Okay, And then we will do, what's that? The time is first, and then index, and then p, right? And then we will sort it, this thing, and then reverse equals true. Okay, so time is first, so we're sort of reversing time. So this is still holds. Tick is -1, 0, still holds. And then blah, 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 we're gonna push what? Heap we want with the smallest, so it's fine. So we can do TIP, okay, equals tasks.pop. Now we're gonna push in something. What do we push in? I like to use tuple. What do we push in? We need to push in the processing time and I, which means the T doesn't really matter, so I don't need to use T, right? So we're gonna push. So if, we check the current tick, the tick is able to, that's actually not right. We shall be while tick is larger equal to this. Pop it, push it. The next one, pop, 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 pop. Get it in, okay? Once we get it in, then we need to pop from the heap, right? We need to pop from the heap. Then we need to check the top of the heap to see what is there, to determine how to progress on the tick. So now we can do, time is still not important, so we can say P and I, right, equal to heap q.heap pop. We're gonna pop the heap, then rest gonna append I and tick plus equal to processing time. And then going back, now we try this again, blah, blah, blah. Once we get out, means we'll push everything in. Then we need to say while heap. Then we do this thing all over again. Oh, while task or heap. Like this. Then we can return rest. All right. Yeah, this is slightly more complicated, but it's quite fun. See, this is a good problem. Very good problem. All right, let's see if we got it right. Tasks. What's this? Get order. Tasks. Damn. What the heck? Not enough value to unpack. Oh, you dumb. You changed it. You changed it to sorted tasks. Yep. I have confidence. Yeah, I have confidence. Let's go for this. Should be right. Oh my god. Huh. Wow, I did not expect this to happen. Holy guacamole. So the heap is empty. And then we have sorted tasks, but we don't have heap? What? What is this? I mean, I could have just added gar, but it doesn't make any sense to me. It could be... Oh, I see what happens. There's a gap. Damn. All right. I don't want to just +1. Gotta be a faster way. Yeah, it was my bad. So we'll do this, right? And then we say if we can say if heap, right? We do this. Else, which means nothing gets pushed in, right? Nothing gets so there are tasks, but nothing gets pushed into this. That means the current time is bigger than the tick. Then we can just say tick equals sorted task -1 0, which means I can set tick to 0 here. Haha. There we go. Yeah, this is a tricky part. The next task doesn't start until later. Yeah, I don't have to wait. We can just set it there. Confident. I'm in. Yes, this one shall be right. Yep. Okay. Not bad, huh? Yeah, I mean, it is bad in this case. Did not, absolutely did not think about this at all. $18.34. Sort tasks by in queue time and use a heap to prioritize smallest processing time. The tricky part is that the current tick might be smaller than the next in queue time. If this happens, simply progressing the tick to that next in queue time. And log n for this sorting, and I'll take on time, and overall is on log n. Okay, so this is done. We'll take a look at the solution. Task in queue, process, and yeah. Push, processing time. This is the thing right here. O1 login. To use A and B. I think they changed. This is like as medium as it can get. If you're asking what is a medium problem, this, my friends, is a medium problem. Like as medium as it can get. It's a good problem. Like it. All right, we have 6 minutes. I don't think I can solve this, but it'll be fun to take a look. Count anagrams. You're given a string. containing one or more words. Every consecutive pair of words is separated by a single space. A string T is an anagram of string S. If the ith word of T is a permutation of the ith word of S. For example, ACD and DF is an anagram of this, but DEF and CAV and ADC BEF are not. Turn the number of distinct anagrams of S. Ooh. Distinct. That's the difficult part. That is the difficult part. Distinct. I mean, when the three are all different, the permutation of this is 3 factorial, right? So that one will be 6. And this we have 3, TOO, OTO, and OOT. So it's 3 times 6. So if I can find unique, right? I can find unique numbers of anagrams for each one, and then we just need to multiply them. Is that right? We just need to multiply them. Yeah, because if we have unique here, no. Oh my god, like if it's hot and hot, right? Hot and hot is not 36. Because no, hot and hot is 36. Because each one is different. And each one of this is different. So that is 36. What about TOO and TOO then? Right, when it's TOO, OTO, and OOT, right? No. It is. If I can find unique for each one, then it is a multiplication. Right? Even if those two words are the same. Yeah, this is 9. This should be 36. Of course, this is 3, right? This is 1. 9, yes. 36, yes. 3 and 1. And what's the difficult? The difficult is finding the unique numbers of permutation of a given word, a given string. Unique numbers. Well, we only have 26 letters, right? So we can count it. So we count it. Then what? Well, we have like how many A's, how many B's, how many C's, right? We have all that. Then we say then what do we say? Unique number of... Oh man, this is a problem. This problem itself. I think I've done this before. How to count the unique number of permutations. Unique numbers of permutation. Yeah, you cannot just put a set. That's not gonna work. That ain't gonna work. I forgot. I literally forgot how to do this. I mean, at most is 26, right? But this has a lot of, it has a lot of combinations. No, I don't think that's the way. We just need to figure it out. We just need to figure it out. And also another thing is it doesn't really matter the words. All we need to find is the unique count of each word, because TOO and ABB, they're exactly the same. All right, so we can find the unique count of each one. We sort the counts, and we turn that into a, I don't know, turn into a tuple. And then if we encounter the same pattern, we can get the value out immediately. So that's not difficult. So now the question is, given a pattern of the count of each unique letter, what is the total number of unique permutations? So this is the tough part. I mean, can we like step by step? Let's say we have K count of one letter, and then we have N count of one, I have M count of the other. When we add this to it, how many unique we have, right? Yeah, let's just say we have 2 letters. Okay, we have 2 letters, and then we have one letter has M count, the other letter has N count. That's what we start with. And if we start with one letter, N count, we only have 1 permutation, right? Which means if it's only 1, we only have 1. Now we have 2, then there will be interesting. So we can have the original letter just go out, and then the new we can go. Let's say let's fill it one by one, right? Let's fill it one by one. So we can fill it at the front. Come here, 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 here. So that's n plus 1 if we add 1 into it. Basically, it's just 200, right? If we have 2 and we add 1, we can have 1, 2, 3 slots that we can put. So that's n plus 1. Then we try to put the next one, right? Because we have multiple. Yeah, let's just do this 200, right? So we can TOO, OTO, and OOT. Then we have another T coming in. Then we have these spots. We can put it here, put it here, put it here, put it here. But then we have duplicates. Yeah, how do we handle duplicate in this situation? Hold up. So we have these 2, and then we have 3 open spots. Now we have 2 T's, right? Isn't that just C3 choose 2? What's C3 choose 2? That's 3. Because we can put TT here. Okay, this piece of paper is gone. Yeah, let's say we have TTOO, right? If you want to find TTOO, what are you going to do? You lay down OO, right? And then after you lay down OO, you have 3 spots for the TT to go, right? You lay down OO, you have 3 spots. So we can do TOTO, because C3 choose 2 is 3. So it can be TT, or TOOT, or OTOT. Which means if I do, let's just stick with one of them. Do this, right? Then this has 3. This should be 9. 3 times 3. I don't know what you're doing, man. It's not. Huh? Oh, yeah, that's not right. I'm thinking about on one of them, okay, and then TT can be together. That's right, they can be together, so we can do, oh god, TT, OO, OTTO, and OOTT. Yeah, that's 6. So what do you learn? What do I learn is don't know, man. Yeah, that's just TTOO, right? What if I have 3 T's? What if I have 3 T's? So again, I have 3 spots. I have 3T, right? We can say 3T all together. That's 3. We can say 3T is TT and a T, right? 2 and a 1. That is that going to be 6? Because it's going to be TTTO, right? TTOOT, and then OTTOT, and then the TT and O, they can swap, right? They can swap. Yeah, so that's 6. And then we can split into 3. And that's 1. Or that's 10. So if we do this, it shall be 10. What if we add another T? Now we have 4 T's, right? 3 spot, 4 T's. Again, 4 T's together, split into 2. Now, when we split into 2, there are 2 possibilities. We can do TTT and T, or TT and TT. So TTT and T is going to be C3 choose 2 times 2. I mean, in that case, isn't that just... Yeah, C3... Because they can permute, right? They can permute. Like each thing when they done, they can permute. So it's basically 2 factorial, right? So 3 times 2, that's 6. And then TT and TT, this permute doesn't work, so that's a 3, right? And then we can do 3, right? We can split into 3. That's gonna be TTTT. Man, this doesn't feel right. It doesn't feel right at all. We're seriously analyzing this thing. But is that a repeating problem? Alright, I gotta think about this again. Yeah, I don't want to keep doing this. There's no point. I'll see you guys tomorrow. Adios.